All right, now we're about to begin our first big algebraic section. On question 43 through question 49, solve each equation for x. So before we start giving some tips and tricks here, I'm going to start with this. I'm going to start with question number 50. What identifies each of the above equations as linear equations in one variable? And the reason why is this. When you learn to solve equations in algebra and pre-algebra, you did them in little compartments. You learned to solve one kind of equation, took quizzes over it, took a test, and then you moved on to the next type. After algebra, when you start geometry, all your equations are going to be mixed up. So the very first thing that you want to do is you want to identify what kind of equation that you have, because depending on what kind it is, that'll tell you how you're supposed to solve it. You don't solve a linear equation exactly the same way that you solve a quadratic equation. So most people associate the word linear with its root word, which is, of course, line. And if you have two variables, like an x and a y, and you graph that thing, it does make a line. All of these equations up here, 46, 47, 48, and 49, those are all linear equations. These are linear. But if you were going to graph each one of these, they would not make a line. They're not two-dimensional. And the reason why they're not two-dimensional is because they only have an x. Notice that it says, what identifies each of the above equations as a linear equation in one variable? That's different from a linear equation that has two variables. So when you have a linear equation in one variable, it's not going to make a line. I'm going to make note of that. This is not a line. Even though it bears the same root word when we're talking about the word linear. Instead, algebraically, linear applies to its exponents. And in this case, the highest power is, well, here, let's look back at each one of these. Let's look at each one of these little x's. Every single x, you can see that there's no squares, there's no cubes there. The highest power is implied to be the number 1. If we had quadratics, the highest power would be 2. If you had cubic equations, the highest power would be 3, and so on. So the highest power for linear equations is 1. And when your highest power is 1, no matter how many variables you have, then that thing is called a linear equation. When it is a linear equation in just one variable, you do not make a line. Instead, it's just going to be a single point. It's going to be like x is equal to, who knows, 5. That's not a line. That's just a dot on a number line. That's it. That's all you do. You'd go, here's 0. Here's the number 5, and it's x is equal to 5. It's not the equation like the vertical line x equals 5. It's just a dot on a number line, and that's different from what's happening over here in question 51. When you have two variables and you have an x and a y, when you graph one of those things with an x coordinate and a y coordinate, then of course it's in the coordinate plane, and then you would get something like this, which is a line. And so on 51, you're just giving an example of one of those type of equations. You write the actual equation. That's what it's looking for. So let's look back at these questions as linear equations. Linear equation in one variable. The goal here is to isolate x. Get it all by itself. And the way that you isolate your variables, you do inverse operations. Inverse, remember, just means working something backwards, doing the opposite of what's been done. And you want to try to get the x on just one side of the equation. It doesn't have to be on the left. It could be on the right side if you wanted to. You do the inverse operations to get it by itself. You have 15x minus 17 equals 13. So what do you do first? Do you get rid of the 15 or do you get rid of the 17? Well, I have to get the 15x by itself first before I can get rid of the 15. So that tells us we have to get rid of the 17 first. The 17 is being subtracted, so I'm going to do the inverse of that. I'm going to add it to the other side. Okay, so those are the kind of things that you want to do when you're solving a linear equation. And of course, it gets a little bit more complicated whenever we add in different kinds of numbers, like some decimal numbers, we add in some fractions, and we throw in some grouping symbols like some sort of parentheses here. Okay, so speaking of those kind of things, over here on number 47, notice that we have x's on both sides of the equation. Of course, that makes it a little bit more complicated. So you want to do some combining of like terms before you can isolate your x's. So pro tip here, of course, is that you want to distribute the -6 through the parentheses here. Take that negative sign through it with it first. And when you do, you're going to get -6x's. Notice that this is a -6x, and this is a positive. My tip to you is try to keep your x's positive. When you do, there's less chance of you making some sort of sign error further down the road. So I would suggest adding the 6x's to the other side rather than subtracting the 5x's to the right side on a question like 47. Okay, over here on 48, again, you have x's on both sides, so you want to combine your like terms. And now, notice that the x's are bigger over here on the left-hand side. You've got -6.5. Since it's negative, -6.5 is bigger than -9.7. So if I add the -9.7 to the other side, that's actually going to turn these x's positive. That's not something that you have to have, but it's in your best interest, because then, like I said, further down the road, there's less chance that you're going to make a sign error whenever you're solving that equation. So I would suggest getting this 9x or 9.7x over to the other side by adding it over. Now, one other thing is that when you're in algebra, your teacher probably made this really big deal about doing this kind of thing. So you go plus 9.7x plus 9.7x. And what it's doing is just reinforcing the idea of keeping your equation balanced. That's what the equal sign is all about, that the left side has to be exactly the same as the right side. If you're lifting weights, if you add 9.7 pounds to one side, which is weird, where you get 9.7 pound plates, I don't even know. But if you did that on the right-hand side, you have to also do it on the left-hand side so that the bar stays balanced. Now, what your teacher probably also had you do is draw this little line here so you can cancel these things out, and then you add up your little columns. And some teachers even have you draw yourself a straight line straight down here so you can kind of visualize that equal sign as a wall, bringing things back and forth between those two sides. I don't need to see all of those things. If you want to start practicing doing these kind of things, as in, oh, I know that I'm supposed to add 9.7 to the left-hand side on the x's, and you just do it, I don't necessarily need to see all of the work. And that's something that's going to kind of help you build speed when you're solving these equations. All right, the toughest of the bunch obviously is over here on number 49. What makes it tough, in addition to having some grouping symbols and having x's on both sides, is the fact that you have fractions. So look at the denominators of each of these fractions. Well, that's some strange highlighting happening there. You got a 3, you got a 3, you got a 4, you got a 6. So let's say you were going to add and subtract those fractions. If you're going to add and subtract those fractions, you'd need a common denominator, right? So the common denominator between a 3, another 3, a 4, and a 6, remember the easiest way to do this is to start with the larger of the numbers. And then you see if the other numbers go into it. Well, the 3 obviously goes into it, but the 4 does not. So then you take the next multiple of 6. The next multiple of 6 is going to be a 12. And now check to see, does 3 go into it? Yes. Does 4 go into it? Yes. So 12 is the least common multiple, or the LCD, also least common denominator. And the reason why I did that is because if we multiply everything here by the least common multiple, in this case 12, it's going to get rid of all of the fractions. It's going to get rid of all the fractions, not because the fractions are bad, but because it's going to make this problem so much easier to solve if there's no fractions in it. And the reason why this works is, well, here, let's just take this first, or when I say first part, I mean this last part here as an example. If I take 1/6, it's actually -1/6, and you're going to multiply this by 12, must be 12 over 1. And you do top times top, bottom times bottom. That's going to give you 12 over 6, which is just 2. Since this 12 can be divided by 6, by 4, by 3, then that means it's going to get rid of all the fractions exactly like what happened here. One last thing about this one as a tip, that if you multiply by the least common denominator before you resolve the grouping symbols, the parentheses, do not also multiply inside of the parentheses by the 12. And here's what I mean by that. So let's say that I'm going to take these guys here and I'm going to multiply them by 12. I'm going to take the 12, multiply by, I'll just put brackets around this, negative 1/4 times x plus 6. And so what a lot of people want to do is they want to take this 12 and multiply it times the 1/4, which is what you're supposed to do. And then they also want to multiply it times the parentheses. But you don't, because this is not distributive property. This is multiplication. Think of this x plus 6 as just some sort of number, and you have 3 numbers that you're trying to multiply together. And when you do, that's not the distributive property. You would just multiply these two together, get an answer, and then whatever you get, then you can distribute that to the x plus 6. Here, let me break that down like this. Let's say that I had the number 3 plus 7 plus, I said plus, I mean times, and then times a 4. Now, if I were to group these two up, associate them together, do you take this 3 and you distribute it to the 7 and the 4? No, you do not. The associative property would tell us that you get to do this kind of thing. You can group up the 3 and the 7. I don't know where that little multiplication dot went. You'd multiply these two things together. Whatever you get, then you'd multiply it times the 4. So the exact same thing is happening here. This is not 12 that's getting distributed to each one of these things. Instead, I'm going to associate the 12 and the negative 1/4 and multiply those together to get rid of the fraction. Then whatever you get, you would distribute to the x plus 6.